All right, so we're going to be starting a unit on organic chemistry, which is the carbon chemistry. Carbon chemistry is very interesting stuff, and it is so abundant that you can't believe how much and how many things it can do. All right, so carbon makes macromolecules, which means it can make really long chains of many things. For example, starch is it's so big that you can't really classify it sometimes because there's so many different forms that it can take. But that's a macromolecule. It bonds covalently, okay, covalently, which means that it could be a nonpolar covalent, which we'll see quite a bit, or it could just be polar covalent. All right, so it can be either of those, but it's going to be bonded covalently. It forms bonds to itself over and over and over again, which is, of course, like making macromolecules, and that's called catenation, when it bonds to itself again and again and again. And it forms these long molecular chains that are called polymers. It can bond to all kinds of other atoms, and it can be involved in lots and lots of different reactions. In fact, there's so many molecules, okay, I don't know, that infinite might be too big, but there are so many molecules that some are made every day in maybe the plastics industry or something. And, of course, it's very important to our life processes. And so we're going to start at the beginning here by learning how to draw Lewis dot structures and how to draw these organic molecules. And so we should kind of look at what we're going to see here. When we first start, we'll do something called the expanded formula, where we will input every carbon and every hydrogen while we figure out how this thing is constructed. After you've learned how to do your expanded formula, or even before, you should be able to read the condensed formula. So the condensed formula tells me, based on this structure for a moment, that this group right here is a CH3. You'll see it's bonded to 3 carbons. This group is bonded to a hydrogen and something else. So here's the hydrogen, and here's the something else. In this case, that's a methyl group, etc., etc. So we'll learn how to do this condensed formula, and so you're going to need to be able to go back and forth between the condensed and the expanded formula. Now, there's lots of pictures, or some pictures, using something called the ball and stick model. Mostly we're going to use this to get a sense of the orientation and the direction that the molecule moves in. And so, for example, here's a carbon. It's bonded to a carbon here. In fact, this is all the same formula. But notice that it's also showing the hydrogens that it's bonded to on here. Or here's a carbon, and it's got its hydrogen. So it kind of condenses it so you can see the atoms in a way. And then this structure right here is something called the space-filling model, which is really nice if you're wanting to know something about the intermolecular forces, for example, or what's the shape of the entire molecule. Is it, way long and expanded, or is it really compact and small? So these space models help you see some of these things. And then we're not going to really deal with these right now for the most part, but there is a kind of advanced form that's just drawing lines. So let me see. So if I wanted to draw this structure, well, I'll just do it down here. At every corner and at every end spot, there's a carbon there. It's just not being shown. And however many hydrogens it takes to make this structure. So every spot is a carbon, and whatever number of hydrogens are needed to make the carbon have an octet, which we'll look at more in a minute. So we're not going to really spend that much time with this, but you will see some of these. And then these are the ones that we're really going to spend, at least at the beginning, we're going to spend most of our time on things that look like this. So One thing we can start off by knowing is that carbon is always going to obey the octet rule. Always the octet rule. That means it always has 8 valence electrons when bonded. Okay, so no matter how you go about it, it's going to have 8 valence electrons, which mostly means there's going to be 4 bonds. That can be 4 single bonds, or a double and 2 single bonds, or a triple and 1 single bond. And I'll review all that with you in a little, in fact, I think on the next slide. But my main take home right now is make carbon obey the octet rule. It has to obey the octet rule. All right, so let's recall for a moment how we write Lewis dot structure for just carbon. All right, so carbon has 4 valence electrons, and it's got an electron configuration 1s2, 2s2, 2p2. And we put, remember in Lewis dot structures, you put 1 electron around each side of an atom until you fulfill however many there are. Well, there's 4 valence electrons, so that's the first structure of my carbon. And so now I have an electron available to come in and bond to a hydrogen and form a carbon-hydrogen bond. Okay, so let's move on for a moment and let's look at one we've seen before, CH4. We've drawn that many times. That's 8 valence electrons. If you draw your carbon and attach all of the hydrogens out here and then count your electrons, you'll see there's 2, 4, 6, 8. Okay, so what does this mean in terms of many things? But for example, this is a tetrahedral geometry. It has 4 single bonds. The angles are 109.5 degrees. And remember, this is like a tripod with a camera on top. So if I wanted to draw this in a way where you could see it a little bit, 3-dimensionally, I would draw the camera on top here with the hydrogen and one kind of in the plane there with that hydrogen. Then I would draw 1 hydrogen coming out. This one is coming out towards you and me. And then this one with a dotted line is going backwards. All right, so this is our tripod down here. The tripod are these 3 bonds, and then this is the camera that we're talking about. Okay, so that's tetrahedral geometry, 4 single bonds, 109.5 degrees. And if you'll remember, we had to use valence bond theory to figure out how to make 4 bonds work there. And so this has to have, this has to have sp3 hybridization. So I'm going to take 1 s and 2 p's. 3 p's, and these are the sp3 orbitals, all with the same energy, and I need 4 of those sp3 orbitals, so I can make 4 bonds. What if we, got all carried away there, so let me insert, not this, a blank document. Now let's talk about when we have multiple central atoms. Now, there was a little bit of this in Unit 5 on how we drew structures, but now we really need to understand how to use this. So multiple central atoms, because carbon bonds to itself and other things over and over and over. So let's assume I want to draw something with the formula CH3, CH3. Remember, we just did CH4, okay? And we know that's methane. And we might as well know, and we'll look at this again in a few minutes, that this is ethane. But let's assume I want to draw ethane. So how will I go about deciphering this structure? Well, I know I've got 2 carbons, and so I'm going to bond these 2 carbons together. And then this hydrogen bonded to that carbon. All of those are bonded there. And so I would make 3 bonds to hydrogen off that carbon. And then this, I get a different color, and then this hydrogen on this carbon is also bonded 3 times. So there's hydrogen bonded 3 times here. Let's see. I figured out the number of valence electrons before I started this, but forgot to tell you. There's 14 valence electrons. So I'm going to count and see if I think I've gotten this structure correct. So 2, 4, 6, 8, 10, 12, 14 electrons. That's what I wanted. I have CH3 and CH3. And so this structure, let me redraw this really fast. This structure, and I'm not going to put in the hydrogens. You'll see we get lazy soon. This structure is the same thing as this structure, indicating that these outer atoms are the hydrogens that are bonded to the hydrogen as displayed in this formula, which was CH3, CH3. What about if I have a formula? Where I tell you the formula is C3H8. Now, I've got to figure out how it's no longer in this nice formula where it was condensed and told me what hydrogen went with what carbon. Instead, I have to figure out my chain here. And so, in this case, I know there's 3 carbons, so I'm going to bond them to each other. Oh, let me make a point. Can you ever have a chain like this, where carbon is bonded to hydrogen, and then the hydrogen is bonded to carbon? And the answer is no, 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 no. Hydrogen has 1 electron. Hydrogen forms 1 bond. It is never, ever going to be the central atom. So in these hydrocarbons, you know it has to be a chain of carbons. This chain. Now, I've got 3 carbons as required by this formula. And so I'm going to fill in the hydrogens to make everything have an octet. So I'll put in this H and this H, and then I'm going to put in these, so that's easier to see. These 2 are the same. They're both at the end of the chain. Now this carbon in the middle is bonded to this carbon and this carbon, so it already has 2 bonds. So I can add 1, 2 hydrogens to give this central carbon 4 bonds. That is CH3CH8. Let's count. 1, 2, 3, 4, 5, 6, 7. Oops. What happened here? 1, 2, 3, 4, 5, 6, 7. Oh, it was fine. It's 8. Anyway, this is C3H8. Sorry, I can't count. Now, if I wanted to convert from this formula to where I understand what this says, the structure that it really kind of is, I'd look up here and I'd say, well, I have this carbon bonded to 3 hydrogens, so CH3. And then I have, we'll call this carbon 2. Carbon 2 is bonded to 2 hydrogens. And then carbon 3 is bonded to 3 hydrogens. And that is CH3, CH2, CH3. And the formula name is propane. So, you need to be able to convert between your extended formula, which has all carbons and hydrogens, so you can see it, to the condensed formula, where you can read where the hydrogens and carbons are placed. So that would be the placement of hydrogens with the carbons. And then, of course, there's more like the molecular, or the most simple formula, which in this case was C3H8. All right, now, well, I'll go into that in just a minute. Yeah. All right, so now let's talk about how carbon bonds. All right, how carbon bonds. So carbon can undertake, and remember we had to use valence bond theory because it wouldn't work when we just tried to do VSEPR. Remember, when we have VSEPR, we have 1s2, 2s2, and then the 2 p's. And carbon has this electronic configuration under VSEPR. Well, the problem with that is carbon always forms 4 bonds. Forms 4 bonds. And in this particular case, the best carbon could do in the VSEPR theory is have 2 bonds. So we have instead sp3 hybrid orbitals, and we would just represent those 1, 2, 3, 4, and there's sp3. Now, all of these are singly bonded. If it's sp3, it has 1 sigma bond. 1 sigma bond. And it's tetrahedral. I think we may have gone over this, but let's just redo it. At 109.5 degrees. All right, so those are single bonds. When it's an sp2 hybrid orbital, in other words, there's 1 sigma and 1 pi. And let me show you how that is. We have 3 sp2s here. Each one has an electron in it. And then remember, there's the unhybridized p orbital. And that unhybridized orbital is where the double bond is formed. It comes through here. That's where we form that pi bond. But at any rate, sp2 hybrid orbitals, these are trigonal planar in shape. Or geometry, I guess. They have 120-degree angles between them. And there are sp2 hybrid orbitals. Then there's the triple bond. Okay, in a triple bond, you have 1 sigma and 2 pi bonds. And the triple bond is a linear and 180 degrees. And it has the SPs. There's 2 SPs, each with an electron. And then there's the 2 unhybridized p orbitals. And those form the triple bond. Okay, these form the triple bond. So that's a review of some of the things we've looked at up until now. Now, we're still working on hydrocarbons. Hydrocarbons with just carbon and just hydrogen. And we're going to start with something called the alkane series. And these are all singly bonded, tetrahedral, 1 sigma bond only. And they have this formula, CnH2n plus 2, which we'll look at in a few minutes. Now, I expect for you to be able to recognize and work with every 1 through 10 carbon chain. You should be able to know its name, and you should be able to know the number of carbons. The ones I expect you to be able to work with in terms of converting back and forth and identifying in certain cases are octane. Mostly with nonane and decane, I expect you to be able to recognize them, name them if you needed to. All right, so on an alkane series, everything is singly bonded. There's no double, triple bond anywhere in these. We have this formula, CnH2n plus 2. We have looked at methane, and we looked at ethane, and we looked at propane already. All right, so, and we've seen that, for example, if we do the formula, we did this formula, but if we do the ethane formula, where we have N is equal to 2, then our H's should be equal to 2 times 2 plus 2, which is 6, right? Well, looky here, C2H6. Okay, so you can recognize many things. All right, this formula use is the least useful. It's impossible to tell where anything is bonded in this way, but that is the formula in terms of the number of carbons and hydrogens. And you've got to know these names: methane, ethane, propane, butane, pentane. I want you to notice that every single one of these ends in ane, all right, like the alkane. And then the beginning of this name, if there's 1 carbon, it's a methane. If there's 2 carbons, it's an ethane. If there's 7 carbons, it's a heptane. All right, so you can name these by memorizing them. So, let's see. I want to talk for a minute about another structure. Let me insert a blank page for a second. And let's look at butane. Butane. I don't want to write in red. Butane. Because I have it memorized, I know 2 things. I know it's all single bonds because it ends in ane. And because it begins with but, I know there's 4 carbons. And so when I'm trying to write this structure, the first thing I will do is write a carbon structure. C, 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 C. All right? And then I'm going to add to this all the number of hydrogens I need to make this singly bonded. So, and I'm tired now. I don't want to write hydrogen every time. And so you can see how this gets looser and looser. But I can count that every bond I form is going to hydrogen. So I'll form hydrogens there. And then on the end, I'll form hydrogens here. And then I'll look at this carbon. We'll call this one 1, 2, 3, 4, because we need to learn how to number anyway. So at carbon 2, I'm bonded to carbon 1 and carbon 3, so that's already 2 bonds. That means it needs an H here. Likewise, this one needs an H here and here. And when I write the structure, the condensed structure, it'd be CH3, CH2, CH2, CH3, in order to make all of those singly bonded. Okay, so you should be able to do this up through octane. You should be able to recognize nonane and decane. I also want to look at the structures a different way for just a minute. So here's methane, which we've drawn over and over again with our structural formula showing that it's the Lewis dot structure and there's 4 hydrogen attached to that carbon. And then here's a picture, a ball and stick representation. So the central atom right here is carbon, and then it's bonded to hydrogens out this direction. Now, what I want to note here is more the geometry for just a minute. So notice that this is the structure, that's the tripod part of the tetrahedral, and then up here we have the camera kind of structure. All right, so that ball chain, stick and ball chain helps us figure out sort of the geometry. Here's the ethane, all right, where we have the condensed formula, which doesn't tell us very much. We have the structural formula. We have the molecular formula, and then we have this one, which is more useful, tells us where to put those hydrogens. And this is also all singly bonded. Let's move on to something that's not just single bonds, but instead we have a double bonded carbon. Okay, so the double bonded carbons, remember, they're 120 degrees. And around this carbon, I'll call this carbon 1. Around carbon 1, I have 120 degrees around that carbon. Likewise, on carbon 2, I have 120 degrees between each of the angles. Now, in this case, I have, in the double bond, 1 sigma and 1 pi bond between those 2 carbons. And this is a trigonal planar geometry. We will worry about the reactions with these in a little while. Okay. Let me see. Did I want to tell you something else on here? Oh. Well, I guess I missed that. I'll tell you in a few minutes. Oh, and also, one more thing. This double bond restricts motion. Now, on singly bonded structures, you can have a rotation between the atoms. When you have a double bond, there is no rotation, and this forms a planar portion to whatever the molecule is, because the motion on those carbons is restricted by that double bond. Well, like alkanes, alkenes, also hydrocarbons, just hydrogen and carbon again, have special names. Once again, because of the alkene, you can recognize a double bonded because it ends in -ene. Okay, so if it has 2 carbons, it's ethene. If it has 5 carbons, it's pentene. If it has 8 carbons, it would be octene. Okay, so indicating how many carbons there are. And so I want to, although we didn't really work on these other double bonded ones, I want to look at the carbon with 4, the chain with 4 carbons, that's a butene. Okay, so if we've got butene, we know it has 4 carbons because that's what but means. I don't want to be in red. And we know it's got a double bond. And so to draw this structure, well, let's put in 4 carbons, each bonded one time, 4 bonds to carbon. And then we're told there's an ene. Okay, so we should know right away that there's a double bond. So I'm going to come in here and I'm going to put a double bond right there. Now I'm going to fill in everything it takes to make carbon have 4 atoms. So let's look at these because we've done these. Here's the H's on the end of this group. And then this carbon has 2 hydrogens, our methylene group there. Now let's look at carbon. Let me write these. Let's number these. 1, 2, 3, 4. So let's look at carbon 1. Carbon 1. How many bonds does it already have? It has 2 bonds from the double bond. And so to give it 4, I'll have to give it 2 hydrogens. So this will have 2 hydrogens, and that makes carbon have this carbon 1 now has 4 bonds. What about this carbon 2? That carbon 2, right here, it begins already with 3 bonds. It has 1, 2 in that double bond, and then that bond third. So the only thing this molecule needs, this carbon needs, is 1 hydrogen. 1 hydrogen. That gives everything there 4 bonds. And then you would write this, CH2. CH, there's just 1 hydrogen on that second carbon, and then CH2, CH3. And so in looking at this structure, you'd have to recognize that there's a double bond in there. Now, sometimes people are nice, but not me, and they'll show you the structure has a double bond. Okay, I'm not nice like that. You need to recognize that this is going to have a double bond, so you probably have to sketch this out and look at how many bonds there are and make this into a double bonded if I gave it to you in this form. All right, so I'm not quite done here. Another thing we need to look at is, I'm going to erase this so I can make a point for a minute. And I'm going to rewrite some of it. So C, 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 C. I'm going to say CH2 here and CH3 here just so I'm not interested in that right now. What I want you to see, though, is that I can have the double bond here at carbon 1, 2. I should do this in a different color so we don't have hydrogens and numbers mixed up. Carbon 1, carbon 2, carbon 3, and carbon 4, which have nothing to do with the hydrogens. I can draw a different butene. Okay, I can draw a different butene. And I can draw a butene where I have 4 carbons again. But who said I had to put it on the carbon 1? Couldn't I have put my double bond at carbon 2? That's 1, 2, 3, 4. And the answer is, well, yeah, of course I could have. And when I drew this up, I'm not going to draw it, but you can put in your hydrogens. You should end up seeing this as CH3, CH, CH, CH3. Okay, and that would be its structure. And its name is 2-butene. 2-butene. I would have to name this one 1-butene to indicate where the double bond is. You might see it written, and probably will, as but1-ene. All right, it's indicating that there's a 4-carbon chain. There's a double bond at carbon 1. So this one would also be but2-ene, specifically identifying that the double bond is at carbon 2. And this is a structural representation of 1-butene, where if I number this is 1, 2, 3, and 4. And you can see that this part of the molecule is polar. I guess we can't see it with that color. I'm sorry, this is planar between those 2 carbons. And then even though this one might not look like it, it actually is, these are free rotations down here. While this one is 1, 2, 3, 4, and here's where we have the planar portion of this molecule. And all of that matters to how and when this molecule is reactive and how it works when it does react. Now there's one last series here that, oh no, there's not one last series, but there's a next series called alkynes. Alkynes. They have a triple bond. All right, they have a formula, CnH2n minus 2, okay, and they're very reactive, all right, but they have at least one triple bond. So, for example, here's our 4-carbon chain, 1, 2, 3, 4. When I have a butyne, that means 4 carbons. It's an ine, so I know somewhere I have a triple bond. And in this case, it says so right here at carbon 1. So that's what I've done here. Carbon 1 has the triple bond. I mean, carbon 2 does too, but it starts at carbon 1. And then this is 2-butyne. All right, again, now I know that it's a triple bond, carbon 4, and then on carbon 2, that's where the triple bond is added, right here. And so these are the structures, the ball and sticks, for 1-butyne. Notice it's planar here, and then we get some free rotation around here, and then this part is planar, and then just in case you're interested, this is 180 degrees between all of these 4 molecules, where this is not 180 degrees. This part's 180, okay, but this is not. Then we have something called the alkyne. Oh, this is the alkyne series. So I'm trying to jump ahead of myself. Okay, once again, if we have 5 carbons, we're going to know it's a pent, and because it has a triple bond, it would be named ine. Pentyne indicates that there's 5 carbons in a triple bond and so forth. Then we have these alkyl groups, which I was trying to get to just a minute ago. These are called substituents. Substituents means that we have some long chain of carbons. So we have some chain with all the proper number of hydrogens. That turns out to be hexane. That's as far as I can get. And I would put in the right number of hydrogens and so forth. But what I want you to see here is not in the chain, but attached to the chain is this methyl group. It's like a methane, but instead of being attached to 4 hydrogens, it's attached to 1 carbon on the carbon backbone. There's also this ethyl group, so I could also have a group down here where I would have this CH2, CH3 to the branching off. And then there's more, but there's the propyl. In propyl means a straight chain of 3 carbons. Okay, straight chain. Isopropyl is a little weirder. Isopropyl, we've got some long chain. It goes on and on forever and ever. Okay, all I want to do is look at the substituent here. So coming off this chain is the carbon, this carbon right here, and then that is bonded to CH3, CH3, and 1 hydrogen. And so that's not the same thing as the straight chain. It's branched right here. All right, we'll look at some of this, but I just want you to see what the difference between N-propyl is and something, isopropyl, isobutyl, whatever we're talking about. And then R, my favorite, R just means any hydrocarbon. So if I was talking about the methyl group again, I could indicate, instead of having this chain that I drew out over here, I could use R. R means my chain. And then I would have this little show with a substituent, that it's just bonded to any hydrocarbon, and in this case, my whole chain. Okay, so now that we've gotten to alkyl groups, we need to look at something called isomers. Now, isomers have the same formula. All right, so the structure we're looking at right here, both of these are called C4 or C4H10. Okay, well, that could be butane, because that does have 4 carbons, and if you put it in here and figure it out, it would have 10 hydrogens. So that could be butane, which I've indicated here. So this would be 1, 2, 3, 4. Although there's free rotation around these atoms, between them, they're still just in one chain. So they're still kind of like CH3, CH2, CH2, and CH3. But I also have another molecule, C4H10, and it's not going to be a straight chain with 4 carbons. Instead, carbon 1, 2, 3. All right, so I can see that something's wrong because I don't have everything in I don't have all 4 carbons. So let me try starting here where I had that left off. So that could be 1, 2, 3. Or maybe that might not work. So how about 1, 2, 3? Well, no matter how I do it, this carbon, or wherever I'm looking at, there's 1 carbon that's not in the chain. That's a substituent. This is actually a methyl substituent. So let me renumber so we can start there again. Let's assume that this is carbon 1, this is carbon 2, and this is carbon 3. And then up here we have this substituent carbon. We'll call that 4 for right now. Now, that means that I have a chain of 3 carbons, which I would call propane. All right, there's only three carbons on here. And then, if I look around and I see what this is a methyl group. What's it bonded to? it's bonded to carbon 2. And so I'd have to call that 2-methylpropane. And so isomers, where we have this general definition or general formula, does not help us identify which one possible isomer we're talking about. We need a name, right? A name or a structure drawn out for us to figure out what that might be. And we'll do some more of these, don't you worry. Next, there's the rings, okay, the cyclic alkanes. These are all singly bonded again because they're alkanes, okay, but instead of being in a long chain, they are in a circular or a cyclic fashion. So this is C3H6. That's actually very, very unstable. And if you look at this, here's carbon 1, 2, and 3, and then each one of these carbons, we'll just do this one for example, is bonded 1, 2, 3, 4 times. Okay, so that's great, but gosh, that's messy. And so you can see why people suddenly don't want to write that anymore, and because they know that every corner is a carbon and however many hydrogens you need to make it have 4 bonds. You could also say CH2, 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 and bond like that. Okay. Now, this cyclopropane is very unstable and not likely to stay like that. But it could also be an alkene, so you have to be careful with this formula. This also could be an alkene with a double bond. If I put in my hydrogens, this one will have 3 because it's down at the single end. This one has 1, and you can see I have 3 carbons and 6 hydrogens, so it could be an alkene as well. So you have to be a little careful. Now, we're going to be looking at some of these bigger, they're a little more common and more easily seen. So we'll probably look at cyclohexane and cyclopentane. The way you name this indicates whether it's an alkene or a cyclic structure. If you know it's a cyclic structure, you say cyclo, however many carbons you've got. Then there's another classification of molecules that you'll need to be aware of, and these are those aromatic hydrocarbons. These are rings. Again, only this indicates delocalized electrons. And so we drew this some time ago, way back when we had C6H6. Let me just draw this for you, similar to this one. So now I have 6 carbons. I know I draw terrible. I'm going to put on 1 hydrogen on every carbon because all I have is 6. And then I'm going to see how can I make this carbon have 4 bonds. Well, it has 1, 2, 3 right now. So if I add a triple bond, let's move over here so we can do it in the same place but on the other side. If I add a double bond right there, then that ends up being, once you get this around every other space, and if you count this up, you'll see this works, it ends up looking something like this, where every other side has a double bond. But those aren't really double bonds. Remember, these delocalized electrons have resonance structures, and so it's not just one structure, it's 2 or more structures put together, and these electrons are said to be delocalized over the whole thing. These are in everything, okay? These aromatic hydrocarbons, we see them all over the place, and hey, we can smell them, which is why they're called aromatic. And so for our 6 carbon rings, I just want to briefly show you that this is cyclohexane. It's C6H12, okay? But what I want you to see is this isn't flat. Here's carbon, then it goes down 109.5 degrees, another carbon. It goes up 109.5 degrees, another carbon, et cetera, et cetera. So you can see that this is not flat. It's highly reactive like that. But however, with the benzene C6H6, notice how planar this molecule is. Okay, this one's not planar, and this one is planar. And that has a lot to do with how they react. Oh, and I know you'll be very disappointed to know that that's the end of this. On the next lesson, we're going to learn how to write these structures more systematically using the rules for naming and writing nomenclature. But in the meantime, you need to be studying and know all the alkene, alkyne, and alkyne series, be able to name them for the number of carbons there are, be able to identify that it's got a double or a triple bond, et cetera, et cetera. Guess that's the end.